Hello, I'm Brian Cruz, founder and CEO of New Sapience. Welcome to our Synthetic Intelligence 101 course. Our last session, session 5, was Synthetic Intelligence Origins, and we told the story how New Sapience abandoned the approach of mainstream AI, which we now call imitative AI, and instead of trying to imitate human intelligence and the way human brain creates knowledge in machines, we pursued an entirely different approach, which was to directly engineer knowledge, synthetic knowledge, and put it into a machine. Today, we're going to talk about an issue that has been at the root and a problem with AI from the very beginning, and that is scalability, meaning precisely how much effort does it require to produce an AI application of a given level of performance. And you'll learn today how we solved that. Not only solved it, we solved it massively, orders of magnitude less effort to build a synthetic knowledge application. So our objectives for this course are first to talk about imitative AI and how and why it requires massive resources. Review the scalability issues associated with it. And then, as we look at the New Sapience approach, understand the scalability that comes from using models as opposed to symbols in formatting or creating knowledge in the machine. Understand why and how knowledge is more general than data. And then we're going to introduce a couple of analogies that help understand how the technology works. And that are directly related to scalability. One is the jigsaw puzzle, and the other is DNA. Imitative AI, the first wave, symbolic AI, the second wave, connectionist AI, all require massive resources and massive amounts of computing power and massive amounts of development effort. Just to give you some current examples, Apple's Siri started as a DARPA program. It cost $200 million before it was spun off as a commercial project. Apple acquired it 12 years ago and has been putting millions of dollars into it ever since. And it still clearly doesn't understand a word that you say to it. It's basically just a text command program. But it requires lots of effort, lots of programming to do something useful with natural language when you don't actually comprehend what the words mean. That is, you don't have underlying knowledge of the world in your program. That's why Amazon has had 10,000 people working on Alexa up until very recently. And even so, it has not been a commercial success, because even though they've had all these people trying to figure out what your speech or inputs might mean, it's never gotten good enough that people will actually trust it to order something on Amazon, or very rarely. Instead, they just use it to say, turn on the lights or play something on Spotify. Today's big language models and the generative AI that we're hearing so much about require even greater resources, even in the terms of their energy usage. A startup called Hugging Face is building their own large language model, and they have tried to make it more efficient. They're very proud of how much more efficient they've made it. And they brag that to train their model, only released 20 metric tons of carbon in the atmosphere based on the power plants that were running the servers that they were training it on. And yet none of these imitative AI technologies or applications can really understand a simple sentence. ChatGPT is getting a lot of publicity right now because of the appearance it gives of being able to communicate and transfer ideas from it to you. But in fact, it's an illusion. It has no ideas, which its founders and developers will readily admit when pressed. But perhaps even more important is that even though they require mass resources, doubling or tripling resources does not double or triple the performance of the system. Quite the opposite, in fact. So GPT-3 from OpenAI was 100 times had 100 times more training parameters than GPT-2. GPT 3.5, which is behind ChatGPT, cost $3 billion to develop And it takes millions of dollars a day just to operate, by the way. GPT-4, which is believed to have 100 trillion parameters, 500 times more than GPT, again, it doesn't have 100 times more performance. In fact, it has a little better performance. But these curves, these inverse curves, that is, the performance falls off as you increase the size of the system, is very well known. And it is not much talked about, but it is appreciated and understood by the people who are developing these models. Even 3 or 4 years ago, Jerome Pesenti, VP of AI at Meta, made the comment that they're already running against the wall. Nobody can afford to build these models anymore, or to make them bigger to get much performance, because even though you're making them bigger and bigger, you're not getting that much performance. So he says, in many ways, we're hitting the wall. He said that several years ago. The fact that it appears to be that they have hit the wall, I think, is validated by the second quote here from Sam Altman, the CEO of OpenAI, who just last week said, I think we're at the end of the era where we're going to have these bigger and bigger models. They're already on the flat part of that curve. And he went on to say, we'll make them better in other ways. But in fact, he did not say what those other ways are. The problem is, as we understand it, is the only really other way to make the performance of these big language models better. And here I'm talking about the fact that, quote, they make things up or output stuff that are facts that are not facts, but they're presented as facts, when in fact, it's just a statistical reordering of text in their training sets. So, and of course, there's also the problem that everyone's talking about with bias. Well, the problem is, in order to put any kind of guardrails on that, again, the only thing you can really do is go back to some kind of symbolic program like symbolic rules in AI, and that doesn't scale either. So either way you look at it, they have a scalability problem. And the expectation that they've created that these models are going to get better and better and better until they become true artificial general intelligence, there's really nothing to support that. In fact, there's ample evidence to support just the opposite. Now, Sapiens are based on synthetic knowledge, engineered knowledge, originally curated from human minds, and to a process and tool set that we've created, we make it computable and put it into the computer's memory, where then conventional programming, logic and analysis and synthesis can be applied to extend that model. But what is all important here is to understand that in the past, any attempt to put knowledge in the machine was based on symbols. That was the first wave of AI, symbolic AI. And there's a huge discrepancy in the compactness, the amount of information that is stored in a model versus in data. That's why we have a huge, right now, our society, our technical society is putting out trillions and trillions and trillions and trillions of bytes and bits of data every year, because it's ultimately stored in symbols. If you look here at this example, we have a symbol. It's actually on the left-hand side, a formula, which encodes information about the molecular structure of glucose in this case. On the right, you see a picture of a model of the glucose molecule. And you see immediately how much more compact the knowledge presented, how much more knowledge is presented. And you can ascertain it basically very quickly, because you don't have to go through and decode what those symbols on the left hand mean. So when you're using symbols and you're trying to make knowledge processable in the computer, you're going to have layers and layers of processing to encode and decode the symbols before you even get started. And that, in general, is one reason why our technology is so much more compact. It's the reason we say a picture is worth 1,000 words. Pictures are models. Knowledge has generality. Um, Here is a molecule of knowledge, if you will, using that, continuing with that analogy. And it's a very good analogy because, in fact, this is a very simple picture of our model of the action of riding. What does it mean to ride something? And in that model, we specify what can do the action and what you can do the action to, and what happens as a result of performing that action. And this same little bit of knowledge that is quite easy to capture in our model with the tools we have is reflected in this dialogue with the sapiens on the right, where the human asserts that Jeff rides a cat to work, and it immediately comes back, the system references this model, this molecule of riding, and says, oh, you can't ride cats, and comes back and complains that this doesn't make sense. This is common sense. But the same compact model of the action of riding is used in the second part of the dialogue when the human says, well, Jeff rides scooters to work, understanding that the sapiens didn't know what a scooter was. In this case, he looks at, again, the same little bit of the compact model and can conclude that scooters are probably vehicles, or possibly horses, because horse is also an object. And well, although this picture doesn't show it, there is additional information that most times it's vehicles that you ride and seldom horses or other riding animals. So knowledge by its very nature is general. Now, here's another reason why our applications are so compact and can return so much performance with relatively a very tiny amount of development. So when you build a model using our tools, it's very analogous to putting together a jigsaw puzzle. We've already classified all the core ideas and the component ideas that you need to build out whatever area of knowledge that you're trying to convey or curate from your own mind. So you're starting with pieces, which will only fit together with other pieces in a certain way. And you have an overall map of what it should look like. So that's kind of the picture on the face of a jigsaw puzzle. So when you put together a jigsaw puzzle, if you've ever done that, early on, it's the progress on fitting one piece to another piece and locating that within the overall puzzle goes very slowly. But the more you build that puzzle, the faster it goes, because you can see more and more of the picture, and you have fewer pieces to sort through. So finally, it goes very, very rapidly. And that's just common sense, is that we all understand that the more you know about something, the easier it is to add more to that, because you already have a structure to put new ideas and additional ideas into. And our modeling process follows that exact same paradigm. So our curve is exponential in the right direction, whereas the machine learning, or symbolic AI as well, their curve was exponential in the opposite direction. So in the end, when we talk about the pieces of the puzzle, we've classified what they are, their number, their type, and arranged them into what we call a cognitive core, which is a specification in the computer memory, which determines, through the operation of the program, when more information comes into the system, we can take that information, extract it from encoded symbols in a stream like language, a statement in a natural language. We can pull the word references and align them semantically with model references, which already exist. We know how those pieces fit together. And that process, which is in the incoming side, is called comprehension of language, whereby we take information and convert to knowledge, is really stunningly analogous to what happens in a biological cell when incoming proteins are matched against a specification encoded in the DNA in the cell, and they rearrange to create all of the building blocks of life and all the different parts of an entire organism, all encoded in that very compact specification. So there's certainly a precedence in nature for what we're doing. So it's very much The nodes and the connections that we connect knowledge and ideas together, highly analogous to the chemical and biochemical world. So this results ultimately in a massive disparity in scale. While GPT-3 took massive amounts of computing power, consumed massive amounts of energy, running on huge server farms of high performance computers, months at a time to produce a product output. We have a technology that actually understands what the words mean, understands what's language, and as we can scale it up with a very small team till it has human level comprehension of language in the same sense that we mean. It understands what you tell it and the implications of it. And within 2 months from now, we will demonstrate Sapience running natively on an iPhone. That is the whole package, all the knowledge, all the code, talking to you and talking back to you and understanding what you say to it, running on this iPhone. And so again, the underlying core of this is that it's because of the compactness of models over symbolic representations and the generality at core of knowledge over data. The fact that we've achieved this compactness is proof ultimately that we have created knowledge. And knowledge in that sense, the characteristics of knowledge, its generality and compactness, are exactly the same whether you're talking about knowledge in the human mind and knowledge on the computer. Of course, we don't know how the mind or the brain does it, because we don't understand the brain works, but we do understand how computers work, and we've achieved the same results. So synthetic knowledge is the key to putting the G in artificial general intelligence. And we have a very scalable and a very short runway to taking it from where we are today to the kind of true AIs that people have been talking about for years. Our next episode will be synthetic intelligence applications and markets, where we will explain our plans and vision, how we will take this remarkable technology and get it out into the world. In the end, synthetic knowledge represents a whole new way of programming computers, endowing them with knowledge, not just data and information. And so its applications and markets are huge and will, we feel, revolutionize the way we do technology and the way we use computers. In the meantime, please check out our online resources, newsapience.com, mysapience.com, which gives an insight into our first commercial product, the companion Sapience, my technology blog site, Forward to the Future, and our YouTube channel, where you will find, well, you already know about YouTube channel because you're watching this, probably watching this video on that right now. Also, as you know, we have a crowdfunding, equity crowdfunding campaign going on the Start Engine platform. Anybody can invest in New Sapience. So we hope you will check out that as well. Thank you for your time.